Hey everyone, this is Mr. Sal. This is a quick lesson on graphing quadratics in Vertex form. Thanks for watching. Don't forget to like, comment, and subscribe. Just a real, quick overview of graphs of quadratics. They're not linear. They're called parabolas. So if this was our axis like this, a parabola looks, I don't know, it should look more pretty than that, but that's fine. You know, like a U shape. It can be upside down too. You can get something like that. You know, it just can't be like a straight line or two dots. Does that look like a frowny face now? My bad. I hope that didn't ruin your day. In any case, let's look at just any parabola, something like this. And that would be the graph of some quadratic. The vertex right here is just the tip of that quadratic. You know, it'll look better when you guys do it on the computer. But this is the vertex. Now we usually identify points on a graph, because that's all that is right there, is a point on the graph, as x and y values, but in this case we're going to talk about them as h and k values. Why h and k? I don't really know. Sorry. Maybe vertex in German starts with H or K. I have no idea, okay? But H and K is the letters that we're going to be using for that, especially when we see the formula, all right? The axis of symmetry is pretty crucial. It's going to go straight through that vertex. And for our purposes, it's generally just an up and down line, like this. And so, since it's just a vertical straight up and down line, it's going to have the equation x equals, and then we're looking for the x value of the vertex, which is just h. Here's why it's important that axis of symmetry is because our parabolas or quadratics are symmetric, which means that this point, if I were to look at this point, it would kind of be mirrored along the line to that point. So it's kind of the same distance from that. Yeah, sorry, my drawing's not great. But it's the same distance from that axis of symmetry as the other point on the other side of it. If we were to take this farther away, you know, some point up here, so the distance up is the same for both. So if we went to the left, we'd get this point, the same distance to the right. Again, that's my drawing not being great. But it would be at the same point. Remember, if you miss the line, you just draw the point bigger. Now, you don't have to worry about that so much when you guys are graphing on the computer, right? All it really wants is for you to graph the vertex, and then if you graph any of the points on either side of the line, it'll graph the rest of it for you. Now, when we do this freehand, though, like we probably will on the exam, then we expect you to be able to do that.
Are the orange dots stacked?
The zeros are pretty crucial as well. They kind of help us with writing the equation. Sometimes, and we've seen that before, where they've been called roots. Okay, it's really just the x-intercepts. So that would be these blue points right here, roots. If the vertex were the root, so that was a little bit better, I guess. Let's say that touches that black line. So if that were the vertex right there, then we would only have one root, right? And we've kind of seen that before. So I don't know if we'll see it necessarily in this lesson, but yeah, that's a good question. So this is the standard form for our quadratics, right? ax squared plus bx plus c. And that allows us, if it were in this form, to use the quadratic formula, right? You guys all went home and listened to that song and liked it a lot. Probably not, whatever. In any case, there's just a question on the homework that's going to ask you what A, B, and C are doing, or what it causes the graph to do, okay? The A value, I guess we should look at a graph. The a value will cause the, like if this were our, this is just a general quadratic parabola. A can contract it, so it can make it kind of squeeze like this, but it can also expand it so that it gets wider like that, okay? Now we could, and we probably know this, is if we went from red to purple, that's increasing the a value because it's increasing faster. The values are increasing faster. If it were to go from the red to the green, then it's getting smaller, and we may see some fractional values as the a, which is just the coefficient of x squared. Before we look at b, the b value there, let's look at, on the homework, it's not as important whether it's contracting or expanding as much as if it's making a point up or down, okay? Because if a were positive, then we would get something like the red, purple, or green line. If it were negative, then we can get something that, again, it's opening downwards, like you see on that blue line right there. The c value is going to give us our y-intercept, and we could know that, right, because the x values for the y-intercept is 0. So, I mean, that would make this term 0 and that one 0, and what are you left with? The c value, okay? So whatever the c value is, just the y-intercept, right, wherever it intersects the y-axis. The b value is the slope of the line at the y-intercept. Now, what this generally means is that you guys are going to be seeing these mostly at the y-axis. Okay. Well, all of them will be at the y-axis. I guess what I'm saying is that the vertex will be the y-intercept as well. The reason why this is important, let's say this is my parabola, okay? And but if we took the slope of this parabola at this point, it would be the tangent line that connects to that point. Now the tangent just means it touches it right there, right? At that point, in only one place. The vertex, however, which is very nice, since it's always at the tip of one of our parabolas, is always going to be just a straight across line, like this. And what's the slope of a straight across line? 0. Yeah. The slope of that is 0. So the value of a, b, and c, again, this is just from the homework, it should be either positive, negative, or 0, okay? Maybe it just may ask if it's, well, I guess if we look if it's pointing up or down, or opening up or down, then it will help us out there. So let's start with the a value. This one is opening upwards, right? So that means a would have to be positive. Let's go to the c value, which is the y-intercept. They're at 0, negative 1. Since that's the case, it would be minus 1 right here for c. And so we know that the c value is negative. And then the b value is the slope at the y-intercept, which is the vertex in this case. And since it is at the vertex, the slope at, oh, I should spell that right. The slope at the vertex in this case will be 0. Now there's another way we could do this, is by using the roots, okay? So the roots in this case we see is negative 1 and 1. So we know that the equation would be y is x, and then from the negative 1 we would have x plus 1. And from the positive 1 we would have x minus 1. Okay, we should be at least slightly familiar with that. Not completely because it's so new to us. Well, could we multiply these two so that we have the equation in its standard form? Sure we could, right? This would be x squared minus 1. And we know that pretty quick because they're conjugates. And that, since they're binomials, that means we have a difference of squares. Now if we wrote this in perfect standard form, we'd have x squared plus 0x minus 1. And this shows us the a value, the b value, and the c value right there. That just confirms what we already knew. There's a lot of information in this. This is the general form for parabolas. All right. The reason why we kind of like it like this instead of the standard form is because it gives us the vertex, h and k, and it also gives us the a value, which will determine whether it opens up or down, or how narrow it is or wide it is. Since it also gives us the vertex, we would also have the equation for the line of symmetry, just so we know where that is. Knowing where the vertex is going to help us with graphing as well, because in the past we've kind of started on the y-axis, where y is 0, or x is 0 rather, and then we kind of found x values from there, or we expanded from that point. With graphing parabolas, we're going to be using the vertex and expanding from there. Because it's symmetric, every value as we move away is the same value as we move the other way for the y value. And that's more confusing than it needs to be, but it'll make a little bit more sense when we see the example. If by chance they don't give us this vertex form, which is this, I guess, the formal name for this, we'll have to do completing the square stuff to put in this form. Alright, so graph this. Right. Now this one was already given to us in that vertex form stuff. So let's start with the vertex. Now this is, it's usually a with x minus h plus the k value. That's squared, by the way, sorry. So we see that this h value has to be negative 3, and the k value here also negative 3. So that's our vertex. And we can graph that point, negative 3, negative 3. Okay, now at this point we're going to make a table, and then we'll just put in some values. Now, like I said, we're going to use the vertex to expand on other values that we should be looking at. And we've got t, and then we'll, right, this is a function of t. So we have the t, which is, right, be written as h and k like that. And we have the h value is negative 3. So let's expand from there, meaning I'm going to look at negative 2. And that would be 1 to the right. I'm going to go 1 to the left as well, just to show that it is symmetric, okay? Right, because the line of symmetry should go through that green line. So it should mirror on the left and the right. So if I said that t were negative 2, then I've got 4, oh, there we go, 4 times, now my t is negative 2, oh, there we go, plus the 3, and we're going to square that and subtract 3, right? So now I've got 4, negative 2 plus 3 is 1 squared. 1 squared times 4 is 4, minus 3 is 1. So I have a point at negative 2, 1. So negative 2, 1 right there. Now, since this is on the line of, or across from the line of symmetry, we should get this other point here at negative 4, 1. Let's just confirm that, all right? So I've got 4, and then the t value here is negative 4. And then I'm going to add 3, square that, and then subtract 3. Now, some of you guys know why this is going to work out. It's that squared stuff, right? Because negative 4 plus 3 is negative 1, but that's squared. And by the order of operations, we've got to do that first. So I end up with 4 times 1 minus 3, which is 4 minus 3, which is 1. So that gives me this point, negative 4, 1. Now, since we know that, we won't necessarily be looking at symmetric points. We can just graph them, or we should be able to graph them automatically. Thank goodness this one is not looking for the roots, because it would be really funky values. Well, let's look at one more value just to confirm how this is looking, all right? Because it should just, should curve up like that, right? So let's go to negative 1. Where t is negative 1, you could use 0 if you want, right? So if t is negative 1, then I've got 4 times the quantity negative 1 plus 3, and that would be squared, right? Then we'll subtract 3. Negative 1 plus 3 is 2, which is squared, minus 3. 4 times 4 minus 3. 16 minus 3, which is 13. So that's already going to be, somewhere up in this area. And through the line of symmetry, we should have another point somewhere just straight across from it, like that. So, this then is our graph. Let's see if we can connect these nice and pretty. The computer will graph them better for you guys. Where is the vertex for this? We like these problems, right? So the vertex is at HK, and this is already kind of in vertex form, right? Y equals A, X minus H squared plus K. It's just we got that plus H and then the minus K stuff, right? So we could change this into the A value, by the way, is only going to matter because it's going to tell us which way it opens. So, well, let's answer that first, I guess. The A value is 4, and that's positive, so it's going to have to open upwards. And then we'll make this minus negative 4, right? And that's squared. And then this would be plus negative 2. So again, I'm just writing it like this so we can see exactly what the H and K values are. So H is this negative 4 here, and K is the negative 2. Again, we're just basing that off of the vertex form. The quadratic function has its vertex at the point 4, 3. The function passes through the point negative 2, 1. When written in vertex form, the function is that stuff, right? What they want us to do is write this actual vertex form, given this information right here. The good thing is they gave us the vertex, so we can at least write that in. So we see the H value is 4, so we'll just plug that in. And then the K value is 3, and we'll plug that in. We just got to figure out what the A value is, right? The good thing is that they gave us another point that it goes through. And we've kind of seen this with, well, we've done it with some classes with slope and 980 stuff. What we know here is that f of x is actually the y value. And so I'm going to replace f of x with the y value and the point that it gave us. That's not the vertex, okay? And that would be negative 1. And then the x value in the formula I'm going to replace with the x value it gave us, which was negative 2. Now that negative 1 would equal the a value, which we don't know yet, so I'm just going to keep it as a. And then this is in parentheses, that x value, and it's minus the h value we already have, which is 4. And we're going to square that quantity, and we're also going to add the k value, which is 3. So this is now just an equation with one variable. I mean, there's some more functions in there. Well, let's do that then. So the order of operations, we'll start with the parentheses. And negative 2 minus 4 is negative 6. All right, negative 6 squared is 36. And that's multiplied by the a, right? So I'll just write it as it is. I'm going to just rearrange that so that it's 36a. So it's something that we're used to seeing. Now we'll subtract 3 from both sides. We're just solving for a. And then finally, to solve for a, we would divide both sides by 36. So negative 4 over 36 is going to simplify to negative 1/9. That's our a value, which I can plug into the original formula that we had there at the top. And, well, that's it right there. Oh, it's negative, right? My bad. Determine the domain and range for the graph, and we'll write the answer in interval notation and set builder notation, which we've kind of seen problems like this before. The domain is the x values. So yeah, we'll have to write these with x's, at least for the set builder notation, not necessarily for the interval. Just so we see that, right? I mean, the x values, it starts farthest to the left, it goes is -2, right? And since that's a closed circle, that's included. So as interval notation, it starts at -2. And then how far to the right does this graph go? And we got to look at it one dimension at a time, right? Well, it goes as far to the right as 3. So we got comma 3. That's a open circle though, so it's not included. So in set builder notation, we do need fancy brackets. And we're using x because we're in the domain. We just need the inequality for this. Once we get that, then we're going to close it with some more fancy brackets. Hopefully yours look more fancy than that. All right, and we are comparing x value. And just from the interval, we know it starts at -2. But then it goes to the right, so it has to be eating the x. And also, the -2 was included, so it's also equal to the x.
Is that a 1?
Well, just on the other side of that, we know x goes as high as 3, but it's not included. And it has to be everything that's less than 3, until we get to -2. And that would be the domain for this graph. The range, y values up and down. So, in interval notation, we usually start with the lowest value, right? So how far down does this go? Well, y is -5, very good. It's an open circle, so it's also not included. And then it goes all the way up here, and then it comes back down. But again, we're concerned with how high it goes. And it goes as high as 4. Now that line is touching the 4, so it's also included. Set builder notation, we need our fancy brackets. But again, now we're looking at the y values. So y is a value such that y, it goes as low as -5, which means it has to be greater than that. -5 is not included, so it's just -5 is less than y. But we'll also compare y with its highest value, which is 4. And again, we can see that in the interval. And we'll close that with fancy brackets. We just need the inequality between those two as well. Well, 4 is the maximum, so y has to be less than 4. But since 4 is also included, it could also be equal to 4. Write an equation for the function graph. All right. Well, there's a couple ways we can do this, and I would just prefer to do it the way that we've already seen, and that was in Vertex form, right? In fact, I want to say, yeah, the homework will want this in Vertex form. So, just looking at Vertex form, well, we know from Vertex form the h and k value is just from the vertex, right? So, we can see the vertex, the very tip of that is right here at this point at -2, -1. Okay, so I'm going to go into our form and replace the h and the k value with the values we have right there at -2, so I'm going to make that x plus 2, and then the y value, the h value, is also a negative, so we'll just make that -1. So again, just like we had in that other problem, is we're just missing that a value, and we'll do it the same way though. So we just need to identify any other point on this line where we can find the value of the x and y's, or we can confirm them, right? I'm going to use the y-intercept just because it makes the x value easy, right? So that would be at 0, -3. So again, I'm going to replace my x value with the x value I have here, which is 0. The y value I'm going to replace with that -3. The rest of it's going to stay pretty much the same. Okay, so order of operations, we got the parentheses, 0 plus 2 is 2. Now the exponents, 2 squared is 4. I'll write that right now as 4a. Well, then we'll add 1 to both sides of the equation so that we isolate our 4a, and now that's -2. Divide both sides by 4. And that gives me my a value at negative 1/2 if we simplified that. So in my original equation, I can replace that a value with that negative 1/2. And that's it. Let's do it. So we just want to confirm that we'd get the same equation if we use this point as well, right? And this point is at negative 4, negative 3. So the only thing that changes is, right, these values. Actually, the y value didn't change there, right? It's still negative 3. But the x value did change into negative 4. Well, what's negative 4 plus 2? Negative 2. Then negative 2 squared is still 4.
Okay.
So we can see that it didn't change. It didn't change anything about that. Find the vertex. Well, this is already in vertex form, so that makes it pretty convenient, right? It's already actually in x minus the h value, so we know the h value is 7. The k value, though, we'll need to make, if it helps us, we can see that as plus negative 5 right there. So it looks like it's at 7, negative 5. Bam, vertex, done. If by chance this asked us, does it open up or down? Which way does it open? Down, right? Because our a value is negative. Find the vertex, the x-intercept, and the y-intercept. It's not in vertex form if we look at it just at face value. But we can manipulate this thing, right? Let's see what exactly it is that vertex form looks like. All right, so this is formal vertex form, if that's what you want to call it. But the problem is in our equation up here, we just have the x that's squared. But I guess the question is, could we just make that x minus 0 squared? Sure we could, right? And if we did, we could see that as 9 times the quantity x minus 0 squared. And then, well, yeah, we could make that plus negative 9 if it helps us. So this is just to show the vertex value, which is at h at 0, and then the k value at negative 9. There's our vertex.
Right, explain 0.
All right, from there, let's go ahead and find the x-intercept. Oh, okay, the x-intercept. Yeah, it should say x-intercept, which is kind of weird because they put y-intercepts. Copying and pasting is kind of bad sometimes, right? Let's find the x-intercepts for this, okay? To do that, we know at the x-intercepts that the y value is 0, okay? So if I were to rewrite this, I'd have 0 equals 9x squared minus 9. Then I just got to find the x values that work for this, okay? Well, you could solve this. In my head, I did it by factoring, but you guys don't want to see that garbage. So we're going to add 9 to both sides, right? So that we get the x squareds on their own. So I got 9 equals 9x squared. And then I would divide both sides by 9. And I got 1 equals x squared. And if we square root this stuff, right, we got to split it up into 2 separate parts. So I got the square root of 1 is x, but also the negative square root of 1 is also x. And fortunately for us, the square root of 1 is just 1. So x is 1, but also x equals negative 1. 1, 2 answers, which we would expect because it's a degree of 2. Those were the values for our x-intercept. Let's find the actual x-intercepts. So we know we got 0 value for y. We got 2 of these things though, right? And one had an x value at negative 1, and the other x value was 1. These are the x-intercepts. The y-intercept, well, to me it's a lot easier to solve for because we know the x value is just 0. So we got y equals 9 times 0 squared minus 9. And 0 squared is 0. So we got 9 times 0 minus 9. And so 9 times 0 is 0 minus 9, which is negative 9. So the y-intercept would be at, yeah, you guessed it, was right there the whole time. 0, negative 9. Alright, let's graph this one. Just starting with the vertex, right? And this is already, well, it's not actually, I apologize. It should be x minus h. Since it's plus 4, we're going to make it x minus negative 4 there, squared. So we see the h value is negative 4, and again we can make that plus negative 5 for the k value as well. So negative 4, negative 5, and we can put that on the graph right now. Now just so we understand, we can see that the a value is positive, so it should open upwards. So if we're getting values, you know, down here, we should know right away that we're doing it wrong, okay? Well, having this is nice because it should, or I don't know. You guys may find that drawing the axis of symmetry is helpful. Now I like to find or use lower values, so I'm going to move closer to the 0, alright? So in my equation, so I need to choose an x value and then find its corresponding y value in this. And we can see that the x value here, the green point, is at negative 4. So I'm going to move to x is negative 3. So I got negative 3 plus 4, which is 1, and that's squared minus 5. And 1 squared is 1, 1 minus 5, which is negative 4. So I got the next point at negative 3, negative 4. And again, because of the axis of symmetry, I know I could, well, I guess we can look at this a little bit deeper, right? I went to the right one, and then I went up one from the vertex. So from the axis of symmetry at the vertex, I can go to the left one and then up one as well. And that would be its corresponding symmetric, mirrored, reflected point. So one more. Let's go into negative 2, where x is negative 2. So again, I can go back into the equation. And then let's just, solve this thing. So when x is negative 2, y is negative 1. Now again, I mean, you could go from the vertex if you want, but you can align this with the axis of symmetry. This point is 2 to the right from the axis of symmetry. So the other point, its reflected point, would be 2 to the left, right here. Now if you wanted to show the other points, you could, but on a test this would be just fine enough to draw the parabola.